Um, you don't get to do, what do you look at? Course materials? Is this the way you come in? Content? Does anybody ever provide you with rubrics? Really? That seems so grade 3 to me. I don't. Anyway, so here we are. So if you look at what I told you from the very beginning, how the course is structured, it's going from 0 dimensions up to arbitrarily many. And in some peculiar cases, like kernel principal components, off to infinitely dimensional spaces. And that if you look at it this way, the course kind of hangs together, beginning with the 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional, beyond 3, and then, geez, can we get that down again? Okay? To reducing dimensionality. This stuff, the reason when I've organized it in this way is the stuff that you're looking at here when you're thinking about 0-dimensional data, it's the same things we're going to be looking at higher up because we always have smaller dimensions that we're trying to represent with glyphs or whatever. So looking at numbers and tables, how to arrange tables, again, that's getting into layout, which is a lot like our scatter plots and other things. In 1-dimensional data, we didn't get very far in the, how far did we get on the midterm? We get through just, sorry? Right before categorical? Okay, so we got all of this stuff then. So looking at the numbers in order, you know, how good are quantiles compared to other things? Compared a lot of different sorts of traditional statistical methods that you've seen, some of them since you were in primary school. And also looking at how we're going to look at distribution functions, thinking about that. A distribution function then being something we'd like to estimate. So we're looking at histograms, and any of our plots are effectively models of an underlying density or an underlying distribution function. And you want to think how good are they at capturing that. So there are problems with box plots, not so many problems with quantile functions, looking at histograms and then density estimates, average shifted histograms. So there we could actually do something a little bit mathematical. So the first stuff is all about, a lot of it's about just perception, you know, value of color and length and position along a common scale and area and orientation, all that stuff. How good is it in sort of distinguishing values? And building that up to do some bit of mathematics on density estimation. And then here is looking at far more statistical sorts of ideas. You know, visual comparisons now. This gets a little richer as we get a little more statistical. And thinking about, you know, comparing distributions, actually doing hypothesis testing. So again, statistical ideas, but all done with visualizations. So perceptual, begin to get statistical with estimates, thinking about tests of hypotheses, what's better than another, looking at comparing it to, often you have got hypothetical distributions that you're interested in that the data may or may not come from because you're interested in modeling that for other purposes, often related to richer models where you've assumed some particular distribution. You need to be able to check whether in fact that's the case. Same sort of things can be used for comparing one sample to another. And then started looking at ordering. So ordering became an important theme, the order in which you present things, whether they're side-by-side box plots, side-by-side histograms, whatever they are, some order, because the nearby comparisons are the easiest to make. Okay? Then we get up to two-dimensional data. So again with order, just introducing time. Talked a little bit about time and time series and how to how to decompose time series, how to decompose them into seasonal trends and residual, right? How that actually generalized to think about just a smooth, trying to find the smooth structure in a scatter plot. Can you decompose a scatter plot into, a large bandwidth smooth, then take the residuals, do a slower bandwidth smooth to try and get some interpretability? Can you transform the data? Looking at simply the one we looked at a fair bit was power transformations, but also remember that taking the rank is a transformation. Taking capital F inverse of something is which is roughly the same as that information. Getting capital F inverse should be a uniform, right? That allows us to look at whether or not some variates seem to be independent of one another. Right? Plots of ranks versus ranks are a much better way to tell whether or not there's any dependence between variates. Because you're looking at departure from uniforms. You can set up visual tests of independence that way. And then categorical data, we spent some time talking about different graphics for categorical data, looking at everything from pie charts to bar plots to icosograms to mosaic plots. And what are the differences and common things between them? The icosogram really connects well with probability and conditional probability and independence and conditional independence, so it's a handy thing to think about. And embeds Bayes' theorem, so you can flip back and forth between these things. So for reasoning like we did on the green cab, blue cab problem. And just as with regular data, we could actually look at icosograms for categorical data if we're trying to assess independence, and do that in a lineup plot. Okay. And then the thing is, each time I add a little more. Like, so we went from one-dimensional to two-dimensional. Well, how do we do that? We're thinking about comparing distributions. That's kind of two dimensions you've got going there. Also introducing time, because you always have time as another variable, or at least the order in which the data come to you. And now we're looking at maps as a place where people have often added more information. So what are the characteristics of maps? How do we have people add information to maps? And we looked at pros and cons of using just particular location points versus choropleth maps. Looked at linked micromaps. Looked at conditional choropleth maps. Right? Looked at fitting models based on that. In the assignment, we looked at some of the bad parts of using a choropleth map, to try and infer a choropleth map based on arbitrary political boundaries to infer sort of spatial distributions. And you compare that back to that census data that we had, the American census data that we had, where we had points for each individual roughly, so you could actually see a lot more. That we weren't nearly as contaminated by these arbitrary political differences. So getting from maps, and maps use these polygons for location, which is not such a good idea when it's arbitrary. Use glyphs of various sorts. So we talked about different kinds of glyphs that they tend to use in maps. Use contours. Use sort of changes in color across things. So all of that coming across there was what we got motivation from maps from. And then we thought we could build any kind of glyph we like. So we talked about building glyphs. Glyphs could be histograms, could be anything. And then up to three-dimensional data. In three-dimensional data, we were looking at largely 3D scatter plots, contour plots, all of those same things that we were using from maps up to 3D data. And then we get to use actually motion. So you can actually give the illusion of 3 dimensions. Know the difference between, perspective projections and orthogonal projections. We hate perspective projections because when we're rotating around, at least with orthogonal, we're always seeing a linear combination of the variates. It's always a scatter plot on some linear combination of variates. And your eye can adapt to that. So once we get beyond 3 dimensions, we start thinking about a lot of different things. Some of them are using non-Cartesian coordinates. So we're looking at serial axes, for example. Back up with looking at Nightingale plots. Those plots by Edgar Anderson, just using a glyph that's capturing the data measurements on each point. And then using something like Nightingale's, these stars with the radial axes, parallel axes. There's certain geometry that you can see with those things. What you see in a parallel axis system corresponds to something well known in the Cartesian coordinate system. So you need to be able to move back and forth between those things. You get some value out of the interactive stuff with linking, right? So that you can actually make some connections. And then we started talking about use stars. Oh yes, I started making glyphs that were based on the space-filling curves, making richer glyphs, right? That Hilbert curve and the Morton curve and Kimes curve. And Kime we used on the S&P 500 data where we could see the 3 years. It's very nicely organized. And then we started talking about projections and what are interesting projections. Got us into measures of interestingness like skagnostic measures, how we might lay those out using the skagnostic measures to find the most interesting things first off, just like we did back when we did comparing distributions and used the significance level to order things, comparisons. We could use other measures of interest, these skagnostic measures. And we talked about laying out lots and lots of plots. So you're looking at pairs plots. What are the advantages of a scatter plot matrix or a pairs plot versus, say, a Zen plot that can lay things out in an arbitrary way and have either larger displays or more displays in the same area. And again, using skagnostics there. So projections. And then we've just done a lot of reducing of dimensionality. And the dimensionality reduction, I think, for the methods I've chosen to show to you, they hang together on the principal component analysis. So you got principal component analysis, understand that. Understand the connection between principal component analysis and the Graham matrix, which gets us to inner products, that gets us to any arbitrary inner products, so any kernel, where we know, so we go up to higher dimensions. And also gets us to think about the connection between the Graham matrix and the matrix of squared distances. That allowed us to produce some lower manifolds. Then take that same idea in this funny way of doing local fits like we did with LLE, which is a lot like isomap, but it clearly has different embeddings. But similar kind of idea that we're trying to capture the local structure. So in 15 minutes, that's the course. I think that my advice is that you sort of go through all of this stuff and make a summary of the ideas that matter in each one of these collections of slides. Get this reduced down, right, to 20 pages of material. Take the 20 pages, reduce it to 10. Take the 10, reduce it to 5, 5 to 2, 2 to 1. Get it down to 1 page. So I said throughout this course, there's less here than meets the eye. But I think I try to make it should hang together. And that there's this journey we've gone from, looking at one little number and thinking about how the brain works and how we're wired to see things. And some ways of encoding that information are better than others, to infinitely dimensional, infinitely many numbers on many thousands and thousands of individuals, and can we see any structure? Can we test for structure? Can we estimate that? That's the second time that Java thing's come up during a lecture. And you can see that we're just beginning. Like once you've got all these tools under your belt, and I encourage you to go and play with the software and fool around. I mean, I can't ask you to do everything on assignments. And this last little one, think about how you would do this with the S&P 500 data, something like that, or any data set that you want to play with. So think about that you're recording information, you want to be able to extract the information, whether that's individual numbers, surfaces, patterns, etc. You want to have the best way of doing that. That's going to involve human experiments. How do we behave? It's also going to involve some mathematics. We can actually measure bias and variability of things. We can make the choices ourselves to make things better. We can also then look at trying not to fool ourselves with actual statistical tests, with the lineup test and others. And then I can't say enough about interactive visualization for exploring these kinds of things, to actually play with it and look for patterns. And once identified, go back to the context and figure out what's happening. Right? And I try to make that point as well. The context really matters here in a lot of this stuff. Otherwise, they're just sort of points in space. But you are trying to answer real questions about real things. Questions?